Hi, my name is Caitlin Green, and this is my blog over the Chapter 5 textbook problems. As you can see, like in my previous videos, I do have the questions, the blank questions on the screen, but I will be using my completed sheet here to explain how I got my answers. So the first question is fairly simple. It asks us to expand the binomial p plus q to the 8th power. And very simply, I did that by constructing Pascal's triangle. And whenever I did that, I essentially just found what number of trials t was for 8, and I expanded out the binomial as such. It's a mouthful, so I'm going to put it on the screen. And essentially, I just looked and found on the 8th line of Pascal's triangle, the numbers go 1, 8, 28, 56, 70, and then goes back down. And I essentially just plugged those exponents in. And then for the rest of the binomial, I did say p to the 8th, and then I added 8 plus p to the 7th times q to the 1st, just making sure that all my numbers added up the way they were supposed to. And the rule that I found for obtaining p and q is just simply like, to obtain the power of p and q, both values have to add up to nt. So in this case, our nt was 8, and so say for example, if we had 56p5, q would have to be 3 in order to add up to 8. So that's number 1. Moving on to question 2, it says for problem 1, show that p from the triangle nt equals 8 is equal to t and r. And the way that I did that is I simply just found what t to the 8th power, or excuse me, 2 to the 8th power was, and I got 256. And on Pascal's triangle, it does show you that t equals 256, but just to verify that, I took all the exponents, or excuse me, not the exponents, but the coefficients from the first problem, and added all those numbers together. So 1 plus 8 plus 28 plus 56 plus 70, and then go back down, and I got 256 for that answer. Question 3 is where it doesn't really get a little more tricky, but it is a bit of a longer problem. So it's assuming an unbiased coin, which just means that it isn't rigged and you should have a 50-50 shot either way. What's the probability of getting 8 head tosses, or getting 8 heads and 8 tosses? And these questions were pretty simple because if you used the expanded binomial from before, you can pretty much just plug in your values that way. And since it is 0.5, you can use the binomial rule rather than having to put in each individual value. So for 8 heads, I simply just found the probability of 8 heads, which was equal to 1p8, which ended up giving us 1 over 256. So for that answer, I got 0.0039. 7 heads or more on B, and that one's the same idea, except you have to add the probability of 7 heads, the probability of 8 heads together. And whenever I did that, I ended up getting 9 over 256, so the probability of 7 heads or more came out to be 0.0352. C is the same kind of concept, but it's wanting to know 8 heads or 8 tails. Well, looking at our coefficients, we see that there's only one chance of each of those, and so we have 2 over 256, which ends up giving us 0.0078. And then finally on D, it's basically just adding up everything that we've done so far, except for adding 7 tails to the equation. And so for that, I ended up doing 8p to the 7th power plus q to the 1st plus 1p8 plus 8p to the 1st and q to the 7th plus 1q to the 8th, which when you add up all of those coefficients, you get 18, and then 18 over 256 gives us a value of 0.0703 for the probability. Moving on to question 4. It says answer the same questions as in problem 3, except where p is 0.7, so it's not going to be a binomial equation. And so it's the same setup as it was before, except this time, instead of just looking at the coefficients, we actually have to put in the values 0.7 for p and 0.3 for q. And so whenever I did it for A, 8 heads and 8 tosses, I got 1 times 0.7 to the 8th power, which gave us a probability of 0.0576. For 7 heads or more, I had the same setup. However, I had to add 8 times 0.7 to the 7th power times 0.3 to the 1st power, so we can have probability of 7 heads, and then adding the probability of 8 heads in there, I end up getting 0.2553. Following that same setup for 8 heads or 8 tails, I got 0.0577, and then for 7 heads or more and 7 tails or more, I got 0.2566. And as you can see here, that is the same concept as the first one, however, we have to put 0.7 in the place of p. Question 5 is basically going over a test trials of 9. So nt would equal 9, and it wants to test the prediction of a or alpha equaling 0.05. So it's to go through the 6 steps of the inference procedure and find the outcome for 7 right turns and 2 left turns. So for that, I had my null hypothesis be the probability of right turns be equal to or less than or equal to 0.5, and then the alternative hypothesis being p, the probability of right, greater than 0.5. Next, we were supposed to find the alpha, which we already had as 0.05, and this is a one-tail procedure, or is it binomial, because you can either go left or right, so you only have 2 options. And so for part 4, I found the probability of 7 rights and 2 lefts to be 46 over 512, which was equal to 0.0898. And on step 5, we have to compare the probability that we found with alpha, and the probability that we found was actually greater than alpha, and so we failed to reject the null hypothesis, which means that the rat isn't turning right more often than it should be by chance alone. So it isn't trained or anything, it's just a really big coincidence. And then part B asks to repeat the procedure except for 8 right turns and 1 left turn. So it's the same null hypothesis and alternative hypothesis setup as before. The same thing with alpha. However, the probability of 8 right turns and 1 left turn gives us 10 over 512, which gives us a probability of 0.0195. So on this one, we reject the null hypothesis because 0.0195 is smaller than 0.05. And so, to put it in English terms, the researcher is correct in his hypothesis that the rat will turn right more often than by chance alone. And as you can see, all of my work is set up such to find out both using the 7-step equation. Moving on to number 6. A gambler buys a lucky coin that is guaranteed to be loaded. So, sorry, I need to scroll that up. He does not know whether it is loaded to turn up heads or tails, and so he tosses the coin 12 times and observes that it tails 10 times and heads twice. So, this question is going to be a 2-tailed test because it wants to know if it is equal to 0.5. And so we have to look at both sides in order to find out our true Z critical score. So the number of trials is going to be N12s with 2 heads and 10 tails. So our null hypothesis is going to be the probability of heads is equal to 0.5. And then, which means our alternative hypothesis just has to be that 0.5 is not, or heads of 0.5 is not equal to that, which means that the probability will just be a different number. Our alpha for this problem is 0.05, and the way that we find the z-score in this problem is we have to find the average as well as the standard deviation. And once we find all those values, I got z to equal the absolute value of 10 minus 6 minus 0.5. And notice we just did 0.10 instead of doing the whole 12 because we're trying to find just that certain value. And then we're going to subtract the 4 from 0.5 and then divide that by 1.73. And we get a calculated z-score of 2.02. To find the critical z-score, we have to take alpha and divide it by 0.2 because it's a two-tailed test, and we end up getting 0.025. And after that, we have to go and look in the table D in the column C, and we end up finding that the value of 0.025 has a z-score of 1.96, which is step 5, and we find that the calculated z-score is in fact greater than the critical z-score. So in this question, we have to reject HO and accept the alternative hypothesis. And we put that into English terms. We find out that the coin turns down tails more often than by chance alone, which probably means that it's just a rigged coin. So I do have questions 7 through 10 left for this textbook vlog, so I will be dividing it up into 2 parts. In this section, we went over questions 1 through 6. In my next video, I'll be going over questions 7 through 10. Thank you and have a good day, and stay tuned for part 2.